Now, ladies and gentlemen, we are going to look at electric fields and voltages and this is the situation where Q1 here is going to be given by negative 0.8 nanocoulombs. Q2 is same value, negative 0.8 nanocoulombs, separated by 0.6 of a meter, and we want to know fields and voltages and forces at point B. That's the calculation. Okay. Now, electric field at point B. We've got to think about, well, here's Q1. I'm going to make a big diagram. Q2. The electric field at point B. Remember, for a negative charge, the electric field points toward the charge. So we're going to be summing these two vectors. The magnitude of the vector is going to be given by, and I'm not drawing an arrow over this because it's magnitude only, K Q2 over R squared, where R, in this case, is the same. We're going over 0.6 up 0.3. Using the Pythagorean theorem, we can get R. We can get a value for it. This is point B. Okay. And we can write down, might as well write down a number. Let's go to our calculator. 0.3 squared plus 0.6 of a meter squared. Take the square root of x. I got 0.671. Okay. And so now we can get the magnitudes. And it's the same thing. Well, actually, Q1 and Q2 are the same values. So your magnitudes will be the same. Okay. Crunch the numbers. The magnitude of E1 equals the magnitude of E2 equals, and crunch the numbers. So here's R squared. Take the reciprocal, multiply by K, which is 9 times 10 to the 9th power, times Q1 is 0.8, change sign, times 10 to the negative 9th power. 0.8 negative 0.8 nanocoulombs. So this is E1 or E2. Okay. Negative 16 volts per meter or newtons per coulomb. Okay. But we need the components. First of all, I think it ought to be pretty obvious that, well, this magnitude is the same. The two angles, these two angles are the same also. So the vertical components are going to be equal and opposite. We will not have any vertical component of the electric field at point B. It'll all be horizontal. There we go. The total electric field will all be horizontal because the vertical components, the vertical component of E1, E2 are just equal and opposite, leaving only the horizontal. Okay. For that, we need the cosine of the angle. So cosine of theta equals, it's the adjacent over the hypotenuse. Well, the adjacent side is 0.6 meters, and the hypotenuse is 0.671. So that gives us the cosine of theta. So E1x is going to equal E2x. They're both going to be negative signs. It's this 16 times the cosine of theta. Go to our calculator. So negative 16 times 0.6 divided by, and I think I have that in memory. I do. Okay. So negative 14.3 newtons per coulomb. The total, of course, is the sum of the two. And just to prevent rounding errors, double check on the calculator. Negative 28.6. Okay. And I'm going to pause this a second. Okay, here's the reason I wanted to pause it. I set up the same problem in the PhET simulations, called phet.colorado.edu simulation. Unfortunately, we're restricted to 1 nanocoulomb. We don't get 8/10 with this program. And when I put my electric field sensor, it's 6/10 of a meter. Here's the scale down at the bottom. 6/10 of a meter away from the two charges. The two charges are 6/10 of a meter apart. 3/10 above and 3/10 below this red line. The arrow points in the correct direction, negative, and there are rounding errors, but we can see we're really, really close. is 35.2 times 8/10, close to what we got. And I've already done the calculations. So you get 28.16, 28.6, 28.2 versus 28.6. I think we can attribute it to rounding errors. We know the direction is correct. So we have a pretty high confidence we are correct. Part B. What is the force? If we put a force, excuse me, oh, let's see. Yeah, I'll erase this little line here, an accident. Okay, the force vector and by the way, writing this as vectors, well, I've just said it's the x component. So we know it's x hat. It's in the x hat direction. Might as well write it down here. X hat being the unit vector in the x direction, negative sign means it points to the negative x. The force is going to equal your electric field times the charge, the test charge, QT. Okay. Now, QT, 1 times 10 to the negative 12th. 10 to the negative 12th times negative 28.6. You can leave it in this form if you want. It's the 4 coulombs times coulombs in the denominator and coulombs in the numerator cancel out. So you're just left with newtons, and it's in the x hat direction. Okay. Once you know the electric field, force is easy. C, voltage. We've already got R. So the voltage total is just going to be K Q1 over R plus K Q2 over R. And Q1 and Q2 are identical. So 2K Q, they're the same value. Remember, this might not be true for every problem. Don't presume Q1 and Q2 are equal. They might be equal and opposite. If they're equal and opposite, voltage is 0. If Q1 and Q2 are equal and opposite, and the distance of point B from 1 is the same as the distance of point B from 2, then you get 0 voltage. Okay, so, and now we plug and chug. Get in the calculator, plug and chug. 2 times 9 times 10 to the 9th times 0.8, negative 0.8 times 10 to the negative 9th power, 0.8 nanocoulombs, and divided by, and R is in our memory. Boom. Voltage, negative 21.5 volts. Double check that, negative 21, yeah, good. Okay. And the work, D. D is real easy. Work is voltage times the test charge. Negative 21.5 times test charge is 10 to the negative 12th coulombs. A coulomb times a volt is a joule, by the way. There you go. Negative 21.5 times 10 to the negative 12 joules. So once you have voltage, it's real easy to get work. Once you have electric field, it's real easy to get force. Last thing to double check is our simulation. See if it makes sense. Let's get our voltage indicator, put it on the same point. There we go. Negative 26.6. Negative, boy, that doesn't sound right, does it? Negative 26.6. Did I do something wrong? Oh, I know what the problem is. I need to multiply this by 8/10. These are 1 nanocoulombs. We're using 8/10 of a nanocoulomb. So negative 26.6 times 8/10. I'm pretty sure I'm going to be really close. negative 21.2, and our answer is negative 21.5. A little bit around it, pretty confident. We'll write on. Okay, that ends this problem.